Today is all about inverse functions. Yesterday we talked about the socks and shoes. How it's a function. I put on my socks and then I put on my shoes. In order to undo that motion, we have to take off our shoes. Notice how the verbs change too. Take off, but you stick with the same noun. Stick with the same noun. Take off my shoes, take off my socks. And that's what we're going to concentrate on. We're going to start with linear functions, easier functions, and then we're going to go to nonlinear function. Like, what about parabolas? What about cubic functions? What about rational functions? Oh. So, we already talked about this yesterday. Inverse relation maps the output values back to their original input values. So, if you have a function and you've got their t-chart, the inverse function actually switches the t-chart. Notice this notation. This notation stays there forever. It's a notation. It doesn't change. I need us to underline something. This means that the domain of the inverse, typo, cross this out, this should be note to self, change the PowerPoint, is the range of the original relation. We're going to talk about domain and range a lot. Domains and ranges. Ooh. Like if I get an error somewhere, I need to make a note of that because then I should not use that number in the other function too. We've got to restrict the domain. All right, and then continuing on. The range of the inverse is the domain of the original relation. So talking about domain and range, let's also circle this. It's a notation. It's a notation. It's like things that have to be put together in order to mean something in math. We call this, so I'm going to say F inverse. Or the inverse of F. It's written as F to the negative 1 of X. It looks like it could be multiplied, but it does not mean multiplication. It does not mean multiplication. This is actually what we did yesterday. I wanted to give you a clear picture of what if we didn't do a line. What if we didn't do a line? So the graph of the inverse relation is the reflection of the graph of the original relation of the line, y equals x. This is what we discovered yesterday. But anybody know what this function is? It's a parabola. Do we know the equation of a parabola? Basic parabola. First off, this original equation is a parabola with the equation y equals x squared. The inverse, whenever you take the square root of anything in an equation, you have to include the plus or minus. So this equation is technically, so the inverse is plus or minus square root of x. So to recap, if the original function is an even power, then that means its inverse will be a combination of two graphs, the positive side of the graph and the negative side of the graph. But we actually realized also that there's a domain issue with the inverse. You can't plug in negative numbers. All right, linears are going to be easy. That's kind of like what we did yesterday. All right, let's see how this is going to work. First off, how we're going to be able to find the equation for inverse relationships. We're going to write the original relation. Ooh. And then we're going to switch the x's to y's and the y's to x's. Why would we possibly do this? So because tabularly, or in their tables, their x and their y columns switch, or we underlined those nice key phrases, the domain and the range switch. That's why in the equation we're going to switch the x's to y's and the y's to x's, and then we will resolve for y. Remember, f of x is the same thing as y. A little star something. F of x is going to be the same as y. Okay, all right. We're going to find an equation for this inverse relationship, or for this inverse relation. So, instead of x, we're going to switch. We're going to switch the x and y. That's your first step. And then we've got to solve for y. So you've got to figure out what's the first step in solving for y. And yesterday we talked about how whenever you take an x minus 8, it just becomes x minus 8. Divide both sides by 4. Ooh. Ooh, I don't like that. I would have just had x minus 8 all over 1, 4. Or we could have, we could do this. I would also be okay with y equals x minus 8 over 4. So either this is okay. Ooh! Ooh! But we need to make sure we put in that this is the inverse. So do it again. So first step in the algebra, we switch x and y. And then we start solving for y. So those of you who chose to do the algebra way, you subtract 12. And then we divide by negative 3. Now you're going to see that we're going to divide each piece by negative 3. Getting us negative 1/3 x plus 4, or x over negative 3. That's also what we talked about. The other way, we could have just left it as, okay, so the inverse is x minus 12 all over negative 3. Those are the same. I'd be okay with both. Yes, put that in. Because if you put it as y equals, excuse me? The reason why we don't want just y equals is because we started out the entire problem with y equals. I want to symbolize that this is not the same y. They are not the same line. They are two different lines. So that's why I want to symbolize it, that they are two different lines. So we'll symbolize it as y inverse. Next. There are many forms to write this answer. So first, switch the x and y. Those of you who are doing the algebra, switch the x and y. Add 4 to both sides. And then instead of dividing by 2/3, let's multiply by 3/2. Oh, there's supposed to be a parentheses here. Whoopsies. Parentheses, just parentheses. Multiply by 3/2 on both sides. We get 3/2 x plus 6, or we went through the other forms as well. And let's note that it's supposed to be y inverse, just to help us recognize the difference. What did I say? 3x, 3 times x plus 4 over 2, or 3x plus 12 all over 2. Any of those are fine. There's some algebra. So yesterday we talked about, okay, the relationship between inverses, a function and its inverse, how graphically they're symmetrical around the line y equals x. Graphically they're symmetrical around that line. Tabularly, they're tables. They're x's and y's switched in the tables. And then, wait a second, with words, we talked about socks and shoes. But then there's also algebraically. We can prove that they're inverses. If you take the composition of its inverse, if you take the function and its inverse composition, either way, either order, you should get x. You should get back to its domain. So we're going to verify that these two functions are inverses. And the way we're going to do that is we're going to compose one to the other. Let's do this with words, and then I'm going to do it in algebraic form. Let's talk about words. In order to do whatever function I do first, like if I do, never mind. I'll look at the algebra last. Let's start with f. Let's start with f's function. We got to figure out what does f do. Whatever it starts with, it just subtracts 3. Now, what is the next function? I'm going to describe it below. Well, it just adds 3. What we're going to do is, if we start with x, will we finish with x? So, x subtract 3, we get x minus 3 in the middle, but I'm going to plug that now into the inverse. If you add 3 to that, you do end up with x. What happens if I reverse that order? What happens if I reverse it? So let's start with the inverse, or my bad, let's start with g. If I start with x, add 3, hopefully we are now to this point where we can see that as x plus 3. Then if you plug it into the next function, subtract 3, and we're back to x. So with words, we are good to go. But now we have to struggle through the algebra. Going both ways, we got back to x. We are going to practice each composition in both orders. Each composition should eventually get us down to x. That's our goal. Each composition should eventually get us down to an x. Those are the goals. You should always know what you start with and then what you end with. We're going to start with this left side. We've got to figure out what it means. I'm going to take g's function and plug it into f. Figuring out g's function is the easier part. We know g's function, I can look at it. It's x plus 3. Or it's adding 3 to its input. This input is going to have to subtract 3. So that x plus 3 will now subtract 3. That's what f does. Notice how it completely replaces f's input. Completely replaces that. And I am left with x. Let's try it again, but going in a reverse order. So now let's start with f's function. F's function is taking its input minus 3. But now I'm going to take this expression and put it into g's function. G's function is add 3. So I'm going to take that x minus 3, add 3. And it does get us down to our original input. I'm going to go with words first. I call it a train because you got to follow each boxcar. All right. Add 3. That is the easier one. But then you got to plug it in to g's function. What happens if you multiplied by 2? X plus 6. Now if we subtract 6, there we go, we see the x. What if I reverse that order? So if I start with the input and multiply by 2, and then subtract 6, we actually end up with g's function. But what if I take that expression and plug it in to f's function? Doop-a-doo. What happens? We do just get to x. Now the challenge is, can we do this with the Greek? Or can we do this, I guess it's not Greek. Technically it's, oh man, hold on a second. What kind of writing is it? Arabic. It's actually Arabic. Is it? Wait, hold on. I'm going to research that. I'm going to research. Hebrew? No, it's not Hebrew. So, with the algebra, let's just review what happens. G of x is 2x minus 6. So, I'm going to take 2x minus 6 and replace the x and f. So, it's going to be 1/2. I'm going to take that 2x minus 6, multiply it by 1/2, and add 3. This algebra, after you distribute the 1/2, ladies and gents, I'm recording, thank you. So after you distribute the 1/2, and then you add 3, we get down to x. If we reverse the order, so now I'm going to take f's function and plug it into g's function. G's function is multiply by 2, subtract 6. Distribute the 2. And then we subtract 6, getting us back to x.